Let's take a look at the integral x cubed times root x squared plus 4 dx. You notice that there's a square root of x squared plus 4 here. That's in the form of root x squared plus a squared. And so we want to use the trig substitution x equals a tangent theta. And so let's do that. Here a is 2, so we do the substitution x equals 2 tan theta. And so this whole thing becomes 2 tan theta cube root 2 tan theta square plus 4 dx. We're going to turn the dx to a d theta at a later point, but let's not worry about that just yet. So this is going to be the integral of 8 tangent cube theta square root of 4 tan square theta plus 4 dx. We can pull the 4 out since it's a perfect square, and when we pull it out it becomes a 2, so we have 16 tan cube times square root of tan square plus 1 dx. And remember that the goal of trig substitutions is to use a trig identity to turn the square root of something square plus or minus x square into the square of some trig function, so we can undo that square root. Here tan square plus 1, if you recall, is equal to secant square, because if you start with sine square plus cosine square equals 1, and you divide everything by cosine square, that's going to give you the identity tangent square plus 1 equals 1 over cosine square, that's secant square theta. Okay, so let's do that before we go on to the dx d theta thing. So let's see, square root of secant square theta would just be secant theta and dx. Now you may want to recall that the substitution was x equals 2 tangent theta. So if x is 2 tangent theta, then dx is going to be 2 derivative of tangent is secant square theta d theta. And so this is going to be 16 tangent cube secant times 2 secant squared d theta. Alright? And we can combine these to get integral of 16 tangent cube secant cubed. Oops, it's not 16, it's 32. I forgot about a 2. D theta. Okay, now the hard part, I guess, or another hard part, is to figure out how to do this integral. Integral of 32 tangent cube secant cube d theta. Well, one way of doing this is, well, let's pull out the 32, right? We don't need to worry about that. We'll write this as tangent secant tangent square secant square d theta. And one reason why I'm doing that is because remember that tangent and secant, or at least their squares, are related through this trig identity. Tan square plus 1 equals secant square. So what I'm going to do is I'm going to rewrite tangent square in terms of secant square. So this is going to be tangent secant secant square minus 1 secant square d theta. And so this is 32 tangent theta secant theta parenthesis secant to the 4th theta minus secant square theta d theta. And there's a reason why I didn't multiply the secant with the tangent secant through into the other secants, and that is, if you remember, the derivative d theta of secant theta is tangent secant. So it's pretty easy to see that the tangent secant on the left is actually sort of the extra factor in some kind of chain rule thing involving secant to some power. Conveniently, we have secant to some powers on the right. So this is something that we can do using regular substitution. In fact, I'm going to do that right now. I'm going to make the substitution u equals secant theta. And so using the purple formula we just wrote down, du is tan theta secant theta d theta, or d theta equals du over tan theta secant theta. And conveniently, you can see the tan theta secant theta will cancel out. So let's go back to the original. Let's go back and change the original integral to u. This is tan theta secant theta. Secant is u, so secant to the fourth is u to the fourth minus secant squared is u squared du. Or let's put this all over underneath here. Tan theta secant theta, and make the integral sign a little bigger. The tan theta secant theta go away. And now this is 32 times u to the fifth over 5 minus u cubed over 3 plus c. Because it's just a polynomial at this point. Of course, u is not the variable we want. U is in fact secant theta, so we want to actually turn this to secant to the fifth theta over 5 minus secant cubed theta over 5 plus c. Of course, theta is not the variable we want, because if you remember, x is equal to 2 tangent theta. So let's write this down here. X is 2 tan theta. That means tan theta is equal to x over 2. So if we draw the triangle, theta is here, x is here, and 2 is here, because the opposite over adjacent is tangent. And so the hypotenuse is root x squared plus 4 using the Pythagorean theorem. And so secant, which is 1 over cosine, cosine is adjacent over hypotenuse, so secant would be hypotenuse over adjacent, which would be, in this case, root x squared plus 4 over 2. Alright, we're finally ready to put everything together. Let's see. This is 32. 32 secant, that's root x squared plus 4 over 2 to the fifth times 1 over 5. Is it minus or plus? Minus secant root x squared plus 4 over 2 cubed times 1/3 plus c. I kind of ran out of room, so I'll put it down here. And so one last thing that I'm going to do to simplify this is just to do 32 x squared plus 4 to the 5 halves. 2 to the fifth, I believe, is 32. And 32 times 5. I could just multiply the 32 through, but I'll leave it out there for now. 32 times 5 is 160. Minus x squared plus 4 to the 3 halves over 8 times 3 is 24 plus c. And if you want to, you can multiply the 32 through, but I think this is pretty good. This is as far as I'm going to take this. So just a review of what we've done. I mean, like, what was the original problem? Alright, integral of x cubed times root x squared plus 4. And the way we did that is we said, oh, root x squared plus 4 is square root of x squared plus a squared. That's the form. So we're going to use the substitution x equals 2 tangent because 2 squared is 4. And by using the identity that tan squared plus 1 is secant squared, we got rid of the square root. Of course, then we had to deal with we had to deal with the dx, turn it into d theta, and finally we have to solve the integral 32 tangent cube secant cube d theta. And the way that we do that is essentially by saving a tangent secant and then turning tangent square into secant square minus 1 whenever, or when we see it, when we have that tangent square. By doing that, we turn everything except for the tangent secant into sort of a polynomial function of secant, and since the derivative of secant is tangent secant, we can use the substitution u equals secant and have the tangent secant in the du over tangent secant cancel out the tangent secant we saved. Ultimately, we got the integral in terms of u, then we did it in terms of theta, then we drew the triangle that associated with our substitution, x equals 2 tangent, and ultimately we replace everything that's in theta by x, or x squared plus 4 over whatever, and this is our final antiderivative.